way she's making
If she were
anyway, physics time. The recording has started. Physics time.
Physics time.
You
time?
How you got?
Physics on.
Okay, physics time. We're talking today about Newton's first law, which is inertia. Let's just get started. We just got done talking about mass and weight. We're going to talk about that a little bit more in depth.
What's your gorilla's name?
Oh, we don't speak of it. Let's recite first in one word. What can I both title this lesson and say is Newton's first law? Inertia. And then now let's recite Newton's first law. You should know it already.
Object in rest.
An object
at rest.
In motion.
Let's start with in motion. That's the way I've always heard it started, but it doesn't really matter. In motion tends
to stay in motion unless, and do you go straight to and an object or?
No, you say unless acted upon, then you say.
Yeah, unless acted
upon by a force or.
Let's specify.
By something else.
An unbalanced, I'm going to say force, because look at this. If I'm just standing here, are there forces acting on me?
Yes.
Yes. Are they causing my motion to change? No. So the forces acting on me are balanced in this case, and we'll talk more about that when we talk about equilibrium. But the forces acting on me are balanced, so it takes an unbalanced force to cause an object to change its motion. And the corollary to this is an object at rest tends to stay at rest unless acted upon by another. An unbalanced force. This relates hopefully clearly to acceleration. We talked about acceleration. Remember, we defined acceleration as a change in what?
Acceleration?
Yeah, it's a change in
velocity and direction.
Velocity, which includes direction. Yes. Acceleration is a change in velocity. We could also describe it more loosely as acceleration as a change in motion. So when we have here a change in motion, it's caused by an unbalanced force. Unbalanced forces cause acceleration, and an acceleration is a change in motion. In the same way that there were two ways an object could have could have no acceleration, what were those two ways? What two states of being could an object be in where it's not changing its motion?
In a straight line.
Moving in a straight line at a constant speed, which is kind of like this top one, or at rest, which is exactly like the bottom one.
Okay.
These two things are directly related to the two ways an object is not accelerating. So if there are no unbalanced forces acting on an object, let's do this. No unbalanced forces. Well, we could say this as what? No unbalanced forces. How else could I phrase that?
No forces.
It could be no forces, or it could be only balanced forces. So no unbalanced forces leads to no acceleration, which leads to no motion? No, that's not true. No change in motion, which means it's either stopped, which I'm going to
moving at a constant speed in a straight line.
Right. Either stopped and put at rest, or moving in a straight line at a constant speed, which means no delta v, no change in velocity. And the converse of all of this is if I can tell an object is changing its velocity, like I'm doing when I wiggle back and forth, look, changing velocity, what does that imply? If there is a change in velocity, what does that mean? There is a change in motion, which means I am accelerating, which means there must be an unbalanced force of some kind or other. In this case, what is the unbalanced force caused by?
You're moving.
Yeah, moving is not a force.
Your muscles.
Yes, okay, so force is exerted by my muscles on the floor, which cause the normal force to increase momentarily, which counteracts gravity, and then when I go like this, it falls. So there's unbalanced forces acting in both directions.
Why do they call it the normal force?
It's just what it is. It's just what it do. It's just that's what we call it. I don't know. It's the same thing as asking why is your name Kai. It's just the way it is. Your mommy said so. So basically, that's the answer to this too. Your mommy said so.
Why is your name?
There are two.
My mommy.
Why is your name Kai?
That's because that's my dad's name, and that's his dad's name before him on back until
it was
before that. Yeah.
But so you know how they had like in olden times your job was your name? Well, would you have been a chemist?
The word Keim is German for sprout or seedling or
saplings
or Yeah, it's presumably a plant grower of some kind. It's also used, the word is actually a cognate with the English word germ, so like to germinate.
God!
We'll resume this another time.
What's printing? Mr.
Okay, so well, before we were so rudely interrupted, I was going to tell you that there are two sections that you need to read that are important, and they were in your Mechanical Universe video. We're not going to talk about specifically for brevity's sake, and they are section 4.2, Copernicus on the Earth, and section 4.3, Galileo on motion. We did talk about inertia. Now, the last thing we're going to talk about is one thing your book talked about is vector addition of forces. For you, write this down. Vector addition of forces. You can head it that way. Vector addition of forces. Basically, it's enough for you to know, since we already worked on vectors with velocity in the last couple chapters. You can add. You should add when you go to add forces together. That you use vector addition. So I'm just going to write that over here. Vector addition, like what we did with the trigonometry.
So use vector addition.
Yeah, vector addition applies to forces as well. There will be vector addition of forces on your test, and there will be on the next test too. In fact, they're more prevalent on the next test. You know what do you need clarification on this? You know what's expected of you?
I sure gosh darn hope so.
I sure gosh darn hope so too. Basically, to run through again, effectively you break the forces that are to be added up into their component parts, add the matching components x to x and y to y, and then determine the resultant from that. So two things we need to talk about still. Your book has these sections. Mass is not weight, and what was the other one?
Inertia.
Mass is not weight and mass is not volume is what it heads it. But really, we talk about this way. Mass is a measure of inertia. A lot of times we define mass as a measure of how much matter is in an object, but guess what? The more matter is in an object, not only the more mass it has, but the more inertia it has. Inertia and mass are directly proportional.
So
Does this mean they're the same thing? No, they're not the same thing, but they're directly proportional. The more mass a crater has, the more inertia it has. Levi has more mass and inertia than Ty does. Even though they got the same shirt on. Inertia is not about what shirt you're wearing. It's about how much mass you've got.
Is mass like volume?
Mass is not like volume.
Well,
Volume is
volume
that's
like how
what's-
much space it
That's what's confusing.
Exactly. So, remember, there is matter in this room. What's all about?
Air.
The air. It's taking up a volume much larger than anything else in here, but it has much less mass. So sometimes volume and mass are related. For instance, if we think about just one specific object, like we have a gold bar and a gold nugget, obviously because they're the same kind of matter, the thing with less volume also has less mass. But that's not necessarily true when you compare different kinds of matter. So a lot of things, the bigger it is, the more heavy it is. And for a certain type of thing, that's true. For any one specific thing, the bigger it is, the more mass it has. But if we compare two separate objects, density comes into play, and bigger objects aren't necessarily heavier objects. The example your book gives is here's a picture of a pillow and a car battery. The pillow is larger, but the car battery is 100 times as heavy as the pillow.
Because
And
it's
then-
more dense.
Exactly. And then the other thing is that mass is not the same as weight. This gets a little bit confusing because even though this is true, we still measure the mass of an object when we use a balance, or when you go to the doctor and they use a balance to measure you. We're still actually measuring the weight. But it works out because on Earth's surface, or really anywhere in the universe, as long as the object is in the same place as the other object you're comparing it to, weight and mass are related. They are, once again, directly proportional, but they are not the same.
I think I just figured out how a scale works.
How does the scale work? It depends on the kind of scale, but how does the scale work?
So like, okay, you step on the scale,
Mm-hmm.
and the normal force pushes you up, and it since if you push against something, it pushes back. on you.
Yeah, what law is that? We're not there
The
yet.
second law.
No.
Third law.
Third one,
Yes.
yes, third
so,
law, yes.
So I was trying to think of how to say that. If you push on something, it pushes back on you. So you pushing down on the scale.
Yes. Well,
with,
in fact,
with the force of gravity.
Yeah, the interaction between Earth and you, the
then-
force of gravity.
So it's measuring the normal force pushing back up on you.
In
and,
fact,
and they're equal.
what it's actually measuring is when you notice it's about analog scale. On a digital scale, it's a little bit different, but on an analog scale, what it actually measures is the tightness of a spring. So there's a spring there. When you step on it, it squishes the spring, and then how tight that spring is changes a reading on the analog scale. So really what's measuring is the spring force, what we call it, but you're very close. Because there's no good way to measure directly the normal force, so we use springs, or on a digital scale, we use pressure sensors, which are actuators. Anyway, mass and weight are directly proportional. The main difference is that weight also depends on, weight is a force, mass is not, but weight is a force that depends on what? Gravity. And since forces are vectors, weight, which is a force, is also a vector. What direction is weight acting? Always on this down, which means towards the center of the earth. Do you have questions about any of this?
No.
Your book talks about then vector addition of forces, which we have talked about. We talked about with velocity, but they also apply to forces. And then your book also talks about equilibrium, which another word, we should just write this down, kind of a little side note, but forces are in equilibrium when they are what? What is the next word I'm going to write? Balanced. Equilibrium just means two forces acting on, in this case, force in equilibrium means two or more forces acting on an object that are equal in size but opposite in direction, so they balance each other out. So here's Levi with his spider lens. And if he has two forces acting on him, gravity and the normal force, that are equal but in opposite directions, F sub n, F sub g, then these are in equilibrium. Questions?